Greetings. In this one, I'll shortly talk about the general linear group and also the special linear group, which are two quite important families of groups. And this will be an intro. I'll show an example for each, or a couple of examples of elements, how they go together and why they form a group. And for next videos, we can talk in more detail about them. So, in general, the notation is GL of n and some field f. Well, this notation can also be written like this, and then the field is here. But yeah, there's more ways to denote it, but mostly what it will contain is the field, or at least the size of matrices considered. So it is a group of invertible n by n, so square matrices, that form a group together. Because they are invertible, we need inverses under, of course, matrix multiplication. So basically what we have is a group of n by n square matrices that are invertible, have non-zero determinants, all of them, and they together form a group. So simplest case are 2 by 2 matrices. So one could have, and now let's think about some matrix that has a non-zero determinant. 5, 4, 1, 2 could work. 10 minus 4 is 6, so that works. So this is an example of one of the elements that the general linear group with n equals 2 over the field of, let's say, I'll do the one over the field of reals has. So what it means over some field, that these entries inside the matrix, inside all the matrices considered in that particular group example, will come from real numbers. That's the point. So we have this. Another element is another matrix, will be 2 by 2 again. And what we'll have is, I can again think of some entries and see, just making sure the determinant is not 0, because if it was 0, then that matrix is not invertible. So that would cause a trouble, and then it would not form a group, or it will not be part of the 2 by 2 matrices general linear group, because it has to contain only invertible matrices and square ones, of course, which we do by default here. Now I take into account the 2 by 2 ones because they're the simplest to give examples of, and also the simplest to verify the determinant is non-zero, and simplest and fastest to invert in case you want to do so, and so on. All right, for our next example, 1, 1 like this, and we want non-zero determinant, so this could be the 1, 2, 2, 1. And then the determinant is going to be minus 3. And we can see, as an example, that I can put them in matrix multiplication. And the result will be, again, a 2 by 2 matrix. So when we multiply an n by n matrix by another n by n matrix, the result of that matrix multiplication is n by n of a matrix. And so what will that be concretely is 7. Now doing matrix multiplication. Then for this entry, it's going to be a dot of this row and this column, so 10 plus 1, so 11. For the second row, we have two entries again. 4 plus 4, which is 8. And then second column like that, 8 plus 2 is 10. So this is going to be the result. And again, we can see that the determinant is not going to be 0 if the determinants of these two weren't 0, because the property of determinants, by the way, and it's a very important thing to keep in mind, well, if this is matrix A, this is matrix B, then the determinant of AB, as in multiplication, will be the product of their determinants. Well, that means that if neither of their determinants is 0, then the result also will not have a 0 determinant. Here we see 70 minus 88. Well, that's not 0, so there's a non-zero determinant. Now, of course, also as a consequence, if one of the determinants is negative, then the product of the matrices, the determinant of that will be negative as well. So that's the point here. And there's going to be inverse for each of them because they're non-negative, they have non-negative determinants, therefore invertible. And Now let's consider one more thing here. So we've introduced general linear groups a bit. Let's take an example of a subgroup of it. So the general linear group, a subgroup of an n by n set of invertible matrices, could be, for example, special linear group. A special linear group, again, usually can be denoted in a similar way. So SL of n and some field f. Again, I'll consider 2 by 2 matrices. So in this concrete example, I'll have SL2 and I'll take real numbers. So with that, we have 2 by 2 matrices, again, invertible ones, because it has to be a subgroup of the general linear group anyway. So all the conditions for the general linear group will surely apply. And it will be picked elements from that. And how are they defined? It's basically the elements from this one. So it's the matrices from the general linear group. So if I want the special linear group denoted as such, and I'm taking this concrete example by the way already, here I could do a general thing, so maybe I'll write it in general terms. So basically this, so special linear group of n by n matrices over, I'll even do it general with the field, so not just reals but possibility of any field. Then what is that? It's matrices from the general linear group of that size of matrices over that field. Such that their determinant is 1. So there's a speciality of them. And an interesting thing again is that this is a group again. It has already been said, it's a subgroup of the general linear group. And a quick way to see that actually, for example, it's closed under matrix multiplication, it's because of the determinant properties. We can go back to that. So determinant of A times determinant of B is the same like determinant of A times B. And if we take two matrices that have determinant equaling 1, wait, by the way, let's take a concrete example. So in general, I have A, B, C, D as four elements in 2 by 2. So I'm considering this real valued matrices 2 by 2 ones, square ones of course. And the determinant is AD minus BC. So what I want is that to equal 1. Then such matrices will be members of SL2R, 2 by 2 matrices with determinant equaling 1. So for that, AD could be, should be actually, well, we can choose almost anything for now. So I could do 5 times 3 minus, and now I have 15, I need 14, so 7 times 2. So an example that will belong here is, for example, so what will belong here? Well, for example, this matrix. So I said that A is 5, D is 3, and so on. I put it here, so 5, 3, and then 7, 2. Well, to check it, 5 minus 14, it's 1 as a determinant. So yes, and this belongs to the special linear group. So special linear group, 2 over reals, let's say. And that's an example. Let's take another example. So again, I want AD minus BC to be 1. So what other option I have? I could do 3 times 1 minus 2 times 1. And that would be, for example, this matrix. So I'll just put it here in the list of what belongs there, kind of. So AD is 3, 1, so this, and then 2, 1. So I could do it like this. Again, 3 minus 2 is 1. So these both have the determinant of 1. And if I put them in product, so these two, if I put them in product, this whole result again will be in SL of 2R. So yes, it's a group. And it's a subgroup of the generally group, and there's interesting properties. There's also a lot of things that we can observe with regards to homomorphisms and so on, which is a thing that I'll go into in some future video perhaps. But for now, we've had a look at general linear groups, which are the groups of n by n matrices over some field, and also example of subgroup of that special linear group, which are a subgroup of the general linear group over n by n for n by n matrices over some field, with the property that the determinant of the matrices that are elements of it is always 1.